So we've covered derivatives, first and second, and we've analyzed a few parametric curves. Let's talk about the length of a curve when we're given a curve that's defined parametrically. So just as a reminder, at some point when we were looking at length of curve, let's just say that's the curve, and we want its length on the interval a to b. The way you start this process, and most processes in calculus, is it's hard to find the length of a curve that's changing smoothly, so just find the length, make a bunch of points as representatives, or as representative points on the curve, and then just find the length of these line segments, and then let the number of subintervals that you divided this graph into, let that go to infinity. So just, again, if you take, let's just call this the kth subinterval, so that would be x sub k minus 1, that coordinate, and that coordinate here be x sub k. We'll call this distance a change in the kth subinterval. We'll call this the change in the y value on that interval. And so Pythagorean theorem would say that this hypotenuse is equal to the square root of change in x sub k squared plus change in y sub k squared. But that's just one subinterval. We're going to sum up all infinite, and we're going to let n go to infinity. So I'm being really crude here, because this isn't really, we've already sort of talked about this, but when you let n go to infinity, you get precisely this statement here, right? The change in x's and change in y's become the differentials. Now that is almost usable, except it's missing a key part. It's missing something key, which is a differential out here. To be a Riemann sum in a proper definite integral, we need that. So here's how we work around it. So right now we've got that the length is equal to this expression here. Now I'm going to leave out the limits of integration. Now I'm going to have express this integral in terms of time. So I'm going to multiply by dt over dt. And by doing that, so and here's what's going to happen. This dt is going to stay on the outside, the top one. This one I'm going to let absorb. I'm going to bring it into the radical. And when you do that, it becomes 1 over dt squared. Distributed to both terms, you get dx squared over dt squared plus dy squared over dt squared. And now we have this dt out here. And since it's an integral in terms of time, now the limits of integration are from time 1, that it corresponds to point A, or the x-coordinate A, to time 2, which corresponds to the x-coordinate B. And last but not least, we'll just clean up the inside here. So this is t1 to t2 of the square root of dx dt quantity squared plus dy dt quantity squared. And now we've got a nice usable formula. This one's easier to remember probably than the other one. But that is the formula for length of a curve in parametric. And when we get to, when we start talking about vectors, we're going to see that this also represents the distance traveled, because if you think about what parametric curves represent, they represent movement of a point through space, and so the length of the curve is also the distance that curve, or that point, traveled on that interval. So let's look at an example here. So these problems are pretty straightforward, especially if you have a calculator. You're just going to apply the formula. So we want the length of this curve when time goes from 0 to 2 pi. We're going to take the derivative of x with respect to time and y with respect to time, and we're going to put those here into the integral. And let's just do that work off to the side here. So dx dt is going to be the derivative of 2 cosine cubed t. So be careful here. That's going to be 6 cosine squared times the derivative of cosine, which is negative sine. So we can write that as negative 6 sine t cosine squared, and dy dt would be 6 sine t squared, or 6 sine squared of t times cosine. So we put those into the integral. So dx dt squared would be negative 6 sine t times cosine squared of t squared, and add that to dy dt squared, which is 6 sine squared t times cosine of t squared dt. Now, to actually evaluate this, I mean, I imagine this probably cleans up pretty nicely. I'm sure there's some trig identities, but let's just use our calculator anyways. You're gonna be in function mode and put everything in terms of x. Just pretend t is x. Now, if you're one of my students and you have a program that does integrals, then what you'll want to do, as strange as this may sound, you want to put this into y2, or what I'd recommend. Put that into y2, that into y3. And then what I would do is I would make y1 equal to the square root of y2 squared plus y3 squared, and then I would integrate using the program I've given you. The reason I have the actual function into y1 is because I don't think the program you have, at least the one my kids have, allows you to select the which y equation you're using. It always assumes you're using y1. So that just means if you're going to do this, you have to make sure you put these guys into y2 and y3. But in any case, I'll just do it using the program on the calculator. So if you notice here on y1, I've put the square root of y2 squared plus y3 squared. In y2 I put negative 6 sine of x times cosine squared of x, and then for y3 I put 6 sine squared of x times cosine of x. And then I'm going to go to the quit screen. I'm going to hit math. I'm going to go down to f function integrates. I'm going to integrate the function in y1 with respect to x on the interval 0 to 2 pi, and I end up getting 12. So this equals a 12, which to me suggests that this really will clean up, because to get such a nice answer probably means that some squares will pop out, and this integral probably turns out to be pretty nice to do by hand. But in any case, there is length of curves for parametric curves.